I would like you to articulate the fundamental differences in design philosophy, safety factors, and stress analysis requirements between ASME Section 8, Division 1, and Division 2.
Certainly. Well, at a macro level, the distinction really comes down to how conservative your mathematics are versus how rigorous your physical analysis is.
Okay, expand on that.
Division 1 operates on what we call a design-by-rule philosophy. It is essentially a blunt, highly conservative instrument,
Blunt in what way?
in that it utilizes massive safety factors on the material's tensile strength, specifically a factor of 3.5.
Yeah.
You are basically over-engineering the thickness of the steel to compensate for highly simplified, generalized calculations.
Right, and Division 2.
Division 2 flips that paradigm entirely. It utilizes a design-by-analysis approach. Because you are actually proving the physics rather than just guessing, the code allows you to drop that safety factor significantly.
Just down to what,
Down to
exactly?
3.0, or even 2.4 for Class 2 vessels. But, to justify shedding all that protective steel, Division 2 mandates rigorous stress categorization using finite element analysis, or FEA, along with exhaustive material testing.
Let's pause and unpack the physics behind those calculations. When you say Division 1 uses simplified calculations, what is the physical reality of that? What is the code actually measuring to determine if a vessel will survive?
Good question. Division 1 calculates the minimum wall thickness based almost entirely on primary membrane stress.
Membrane stress, right?
Yeah, to visualize membrane stress, think of inflating a rubber balloon. As the pressure builds inside, the rubber stretches uniformly across its entire surface. That uniform pulling force is the membrane stress.
Making sure it doesn't pop.
Exactly. Division 1 figures out how thick the steel needs to be to prevent the balloon from popping, which we formally call gross plastic collapse.
But a pressure vessel isn't a perfect, featureless balloon, is it? I mean, it has heavy nozzles cut into it, structural support saddles welded to the bottom, highly complex geometries.
Precisely, and that is the fundamental limitation of Division 1. When you cut a massive hole in your balloon to weld in a heavy steel nozzle, the stress doesn't just spread uniformly anymore.
It concentrates.
Right? It concentrates intensely right at the corner of that joint. Division 1 doesn't bother mathematically mapping every single microscopic stress peak at that nozzle corner. Instead, it simply mandates a highly conservative safety buffer, adding extra thickness globally to blindly cover all those localized unknowns.
So how does Division 2 explicitly handle those localized stresses differently in practice?
By essentially mapping the microscopic reality of the steel, Division 2 explicitly classifies stresses into primary, secondary, and peak categories. Let's use a paperclip analogy.
But
If you gently bend a paperclip just a little bit and let go, it springs back to its original shape. That is elastic behavior. If you bend it extremely hard, it stays bent.
right, permanent deformation.
Yes, that localized permanent deformation is plastic yielding. Division 2's finite element analysis allows the engineer to mathematically prove that under secondary thermal loads, a tiny localized area of the vessel is allowed to yield slightly.
So it can permanently bend.
Yes, exactly. To permanently bend without the entire global structure collapsing. You are surgically proving the vessel is safe, rather than just burying it in thick steel.
I appreciate the theoretical appeal of surgical precision, but let's employ a bit of professional skepticism here and look at the actual economics of a project.
Okay.
If Division 2 acts as an analytical scalpel that allows for thinner vessel walls, it sounds like a guaranteed cost saver on raw material. Why wouldn't a project management team simply demand that Division 2 is applied universally across every vessel in the facility to save money?
Well, if a project manager assumes Division 2 is always cheaper simply because it reduces the physical tonnage of steel, they are walking into a classic engineering trap.
How so?
You can never look at raw material savings in a vacuum. You have to account for the massive engineering overhead required to actually execute that design.
Walk me through that overhead. Where is the actual economic break-even point?
For low-pressure or thin-walled vessels, the cost of paying a team of specialists to run hundreds of hours of finite element analysis, combined with the cost of drafting a legally certified user's design specification, the UDS, will drastically outweigh whatever you saved on buying slightly thinner steel plates.
So the engineering hours just eat the material savings.
Completely. The economic break-even typically only occurs at high-pressure applications. Usually we're talking about anything operating above 20 bar or where the required wall thickness starts exceeding 50 millimeters.
Quantify that for me. Give me a concrete scenario where the math definitively favors Division 2.
Let's look at a heavy hydrogen reactor operating at 150 bar. If you design that reactor under the blunt rules of Division 1, It might require a massive shell thickness of 110 millimeters.
That is massive.
It is. But if you redesign that exact same reactor under Division 2, Class 2, utilizing advanced stress analysis to evaluate localized and cyclic failure modes, you can legally reduce that required thickness down to 82 millimeters.
Wow, that is a nearly 30-millimeter reduction in solid steel.
Precisely. Division 1 protects against gross plastic collapse, using simple thickness formulas and high safety factors, whereas Division 2 permits thinner walls by utilizing advanced stress analysis to evaluate localized and cyclic failure modes.
The cost savings there must be huge.
Right. In that specific high-pressure scenario, the cascading savings are immense. You aren't just buying less raw steel. You are drastically reducing plate rolling costs, because bending 82-millimeter steel is far easier than bending 110-millimeter steel.
Plus the welding.
Exactly. You're shedding hundreds of hours of heavy welding and lowering the massive cranes required to lift the final vessel. Those cascading fabrication savings easily offset the expensive FEA engineering hours.
I accept that macro design logic. But let's pivot to the legal and contractual side. You mentioned the user's design specification, the UDS. What is the critical liability trap an engineering firm faces when executing a Division 2 design?
The liability trap is rooted in fatigue. Division 2 explicitly accounts for cyclic loading. So when an engineering firm drafts the UDS, it must be certified by a registered professional engineer, an RPE.
Someone specifically experienced in pressure vessel design, I assume.
Yes, exactly.
Right.
But more importantly, the client and the engineer must flawlessly declare all transient thermal cycles.
Define what a transient thermal cycle looks like in the field.
It is the physical expansion and contraction of the vessel over its lifespan. Every time the refinery starts the reactor up from cold to 400 degrees, and every time they shut it down, the steel breathes.
It expands and contracts.
Right. If the UDS claims the vessel will only experience 50 startup shutdown cycles in its 20-year lifespan, the fatigue analysis is calculated against that specific baseline.
And if they exceed that?
If the operator actually cycles it 300 times and the vessel experiences a catastrophic fatigue crack down the line, the original finite element analysis is entirely invalidated. The legal liability for that explosive containment failure falls squarely on the owner and the engineer who signed off on an incomplete or inaccurate specification.
Excellent. Next question. Let's transition away from the macro philosophy of the plate steel and drill down into the micro bottlenecks of fabrication. Specifically, how we inspect the joints holding those plates together.
Okay, the welding.
Yes. How does the choice of joint efficiency, denoted as E under ASME Section 8, Division 1, specifically UW11 and UW12, structurally govern the required shell thickness?
Well, joint efficiency is, at its core, a direct structural penalty factor. It artificially reduces the allowable stress of your material mathematically, based entirely on the degree of non-destructive examination, or NDE, performed on the welded seams.
And what's the scale for that penalty?
It operates on a mathematical scale from 0.65 up to 1.00.
Explain how the inspection technique dictates that scale.
Sure, if you choose to perform full radiography, meaning you X-ray 100% of the length of the welded seams to prove there are absolutely zero hidden cracks or voids, the code rewards you. It yields an E of 1.00.
So mathematically it's perfect?
Structurally, yes. The math essentially assumes that your weld is perfectly pristine, identical in strength to the seamless parent metal. This completely minimizes your required wall thickness. However, if you choose to only spot check the welds, maybe X-raying 1 out of every 50 feet of weld, you introduce structural doubt.
And the code penalizes that doubt.
Exactly.
Quantify that penalty for me. If I am an EPC contractor trying to save time on my construction schedule by skipping X-rays, what does the math actually do to my vessel?
Well, under UW11A versus UW11B, full radiography on Type 1 fully welded butt joints gives you that E of 1.00. If you drop down to spot radiography, the penalty reduces your efficiency to an E of 0.85.
So a 15% hit to allowable stress.
All right. And mathematically, that single administrative decision instantly forces you to add roughly 17.6% to your required shell thickness. If you perform no radiography at all on that joint, your E drops to 0.70.
That's a massive drop.
It is a direct, brutal trade-off. A lower joint efficiency directly forces you to buy, roll, and weld a much thicker, heavier vessel.
Let's test that logic against a real-world field scenario. Let's say your procurement team is trying to be clever. They order a fully seamless pipe to use as the main cylindrical shell of the vessel.
Oh, I see where this is going.
Yeah. Because the pipe itself is manufactured seamlessly with no longitudinal weld, they assume an E of 1.0 across the board. To save on NDE inspection costs, they tell the fabricators to skip spot radiography entirely on the rest of the vessel. Walk me through the legal and structural reality of what we call the seamless shell paradox.
That is a fatal flaw in code interpretation and honestly a very common trap. The paradox is the false assumption that buying a seamless pipe magically guarantees a continuous E of 1.00 for the entire vessel calculation.
Because it doesn't.
The reality is much stricter. Even if the main shell is a seamless pipe, like an ASTM A106, its internal longitudinal seam efficiency is inherently 1.00, but that pipe does not exist in isolation.
Right, it has to be welded to the top and bottom heads to actually form a closed pressure vessel.
Exactly. And the moment that seamless shell is welded to a head using a circumferential weld, what the code calls a Category B joint, the structural integrity of the entire system is only as strong as that connecting joint.
Ah, so the weakest link principle.
Yes. If the fabricator performs only spot radiography or no radiography on that connecting weld, the seamless shell's design thickness calculation is still legally penalized. Depending on the exact RT selection per UW12A, you might be forced to calculate the thickness of your highly expensive seamless pipe at an E of 0.85.
So they gained absolutely nothing by ordering the premium seamless pipe because they fundamentally compromised on the inspection of the connecting welds.
Precisely. Joint efficiency is the code's mathematical mechanism for trading off weld inspection costs against raw material weight savings. Let me quantify exactly how severe this trade-off is.
Please do.
Consider a vessel with an internal design pressure of 30 bar, utilizing standard SA 516 grade 70 carbon steel plate. If you pay for an E of 1.00 with full radiography, it requires a structural shell thickness of 22 millimeters.
Okay, 22 millimeters. And if the fabricator gets cheap and opts for no radiography to save inspection time,
Then E plummets to 0.70, and your required structural thickness instantly jumps from 22 millimeters to 31.8 millimeters.
wow.
Think about the physical reality of that. You saved a few $1,000s by not hiring an X-ray crew. But now your entire vessel is nearly 50% thicker. The overall weight skyrockets.
Which means heavier logistics.
Exactly. You now require heavier shipping transport, more robust concrete foundations at the refinery, and exponentially more welding passes to fill those much deeper 31.8 millimeter bevels.
I want the hard boundaries on extreme operational environments now. We have discussed trading inspection costs against steel weight for standard vessels, but if we are dealing with lethal surface containment, say highly toxic phosgene gas, surely we can't just accept an 0.85 penalty to save a few bucks on an X-ray. What is a detailed caution regarding joint efficiency here?
If a vessel contains lethal substances, the radiography requirements of UW11A5B become absolute. Full radiography is entirely non-negotiable for all longitudinal and circumferential seams.
So no exceptions.
0. The joint efficiencies must be maintained at 1.00. A designer must never specify spot or no radiography for a lethal service vessel. Doing so violates the fundamental law of the code and exposes the operating facility to catastrophic mass casualty containment failure. When toxic release is the failure mode, the code offers zero tolerance for structural shortcuts.
Let's pivot again. Another question. We've established the physical thickness of the steel, and we've proven the structural integrity of the welded joints. But now we have to introduce the aggressive chemistry of the product inside the vessel.
Right, the metallurgy.
Yes, I want to challenge you on metallurgical survival. Explain the engineering criteria and material degradation risks that mandate post-weld heat treatment, or PWHT, under Division 1, explicitly when the material thickness falls below the standard UCS 56 thresholds.
The core principle here is that post-weld heat treatment is strictly required, regardless of how thin the component is, when specified by severe service conditions.
So thickness doesn't always matter.
Right. The code provides general thickness exemption tables, but those standard exemptions absolutely do not apply when you are handling lethal substances or operating in severe stress corrosion cracking environments like sour gas, amine, or caustic services.
I'm going to frame this as an accountability gut check. You are the senior reviewer. An EPC contractor submits a design package to your desk. They have completely omitted PWHT on a very thin 10-millimeter carbon steel amine stripper column.
Oh, boy.
Yeah, and the written justification is that Table UCS 56 legally exempts any thickness under 38 millimeters from mandatory heat treatment. How do you correct them?
I reject the design package immediately, and I pull their engineering team into a review because their logic completely ignores the overarching process chemistry.
It's a fundamental misunderstanding.
Exactly. They have fallen into the trap of blindly following general mechanical tables while ignoring service-driven chemical mandates. Process licensor specifications, such as those from UOP, Axens, or NSE, completely override the basic mechanical code limits.
So the amine overrides it.
Yes. In amine, caustic, or sour H2S service, PWHT is absolutely mandatory, even on a piece of steel as thin as a dime.
Explain the physics of why. What is that amine or hydrogen sulfide actually doing to that thin 10 mm steel wall that makes heat treatment so critical?
We have to look at what welding actually does to metal. When you weld two plates together, you melt the steel at extremely high temperatures. As it cools, it shrinks rapidly. This locks in massive permanent tensile stress right at the weld joint.
Like it's pulling against itself.
Yes, it's like pulling a heavy rubber band as tight as possible and freezing it in place. It is begging to snap. In a sour environment, the hydrogen sulfide molecules break down, and microscopic hydrogen atoms literally migrate inside the crystal lattice of the stressed, hardened steel.
Inside the metal itself.
Exactly. Because the steel is so highly stressed and brittle from the welding, it traps the hydrogen. The hydrogen atoms combine into gas molecules inside the steel, building immense microscopic pressure until the steel simply shatters from the inside out. This is known as hydrogen-induced cracking, or HIC, and sulfide stress cracking.
So how does post-weld heat treatment physically neutralize that atomic level threat?
By essentially baking the entire vessel in a massive furnace, usually around 600 degrees Celsius, and holding it there for hours. This intense thermal soaking doesn't melt the steel, but it relaxes that frozen, stretched rubber band.
It lets the stress go.
Right. It relieves the high tensile weld residual stresses down to roughly 15 to 30% of the material's yield strength.
Does this thermal soaking alter the physical hardness of the steel as well? Give me a quantitative example.
Yes, and the hardness reduction is the critical survival metric. Take a thin-walled 12 mm LPG storage vessel operating in wet H2S, sour service. Based on thickness alone, it wouldn't need PWHT.
But because of the H2S.
Right. The 600-degree baking specifically tempers the microstructure, lowering the hardness of the weld zone and the heat-affected zone below 22 on the Rockwell C scale, or 22 HRC.
And what does that 22 HRC get you?
By physically softening the steel to that specific threshold, you give it the ductility it needs to allow hydrogen atoms to pass through without getting trapped and cracking the metal. Achieving that 22 HRC limit strictly satisfies NR's MR0103 and MR0175 standards.
It sounds like the contractor in our scenario treated heat treatment purely as a mechanical necessity for heavy, thick sections, rather than recognizing it as an essential chemical survival mechanism.
Exactly. PWHT is not merely a stress relief mechanism for thick plates. It is an essential metallurgical tempering operation required to neutralize environmental cracking in aggressive process environments. Without it, aggressive process environments will tear the vessel apart on a molecular level.
I want to push this scenario one step further, right to the absolute bleeding edge of complexity, composite materials. Give me a detailed caution regarding the catastrophic risks of applying this intense post-weld heat treatment to clad vessels.
This is where metallurgical survival becomes incredibly delicate. Often, to save money, a designer will specify a thick, cheap carbon steel base plate to handle the pressure and line the inside with a very thin layer of high-grade stainless steel, like an SS316L explosion-bonded cladding to handle the corrosive chemistry.
Right, you get the strength of carbon steel and the chemical resistance of stainless steel, but you still have to heat treat the vessel because of the thick carbon steel base. What is the trap here?
The trap lies in the sensitization range. When you put that composite vessel into the furnace, the designer must verify that the required holding temperature for the carbon steel does not fall within the specific vulnerability window of the stainless steel lining.
And what is that window?
For standard austenitic stainless steels, that danger zone, the sensitization range, is between 425 and 870 degrees Celsius.
What does sensitization actually look like on a molecular level if the furnace temperature overlaps with that danger zone?
Let's visualize the atomic structure of the stainless steel lining as a brick wall. The metal grains are the bricks, and the grain boundaries holding them together are the mortar. The reason stainless steel doesn't rust is because it contains chromium, which acts as an invisible shield across the wall.
Okay, I'm picturing it.
But if the vessel undergoes prolonged thermal soaking inside that 425 to 870 degree range, the extreme heat causes the chromium to chemically abandon its post. It migrates to the grain boundaries and aggressively bonds with carbon, precipitating out as chromium carbides.
So the shield is stripped away.
Exactly. The mortar of the brick wall is completely drained of its protective chromium, leaving it entirely unprotected and vulnerable to chemical attack. You will have successfully relieved the stress in the heavy carbon steel base, but you will have completely destroyed the corrosion resistance of the internal stainless lining. The process fluid will eat right through the grain boundaries in weeks.
How does an engineer mitigate that metallurgical disaster?
You must preemptively eliminate the carbon from the equation. A low-carbon stainless steel lining grade, like 316L, where the L stands for low carbon, or stabilized grades like 321 or 347 that utilize titanium or niobium to lock up the carbon, must be strictly specified prior to fabrication. You have to harmonize the thermal physics across both the similar metals before the vessel ever goes into the fire.
Excellent. Well, I am stepping out of character now to address you, the listener, directly. Take a deep breath because that was an incredibly intense, grueling exchange.
We're going to look at an entirely new ecosystem designed specifically for working professionals to help you master those high-pressure moments. Okay, picture this. You're sitting right across the table from a panel of... They aren't asking about your hobbies anymore. They're dropping you directly into the hot seat to test your true operational readiness. Imagine you're in that interview. The pressure's on. You're facing intense, high-stakes scenarios. In a real-world interview, you need something that prepares you for the absolute reality of the industry, where your split-second engineering decisions have massive financial and, of course, safety implications. And that brings us to this absolutely game-changing app, which is available right now on the Play Store. What we're looking at here isn't just some random list of questions thrown together. No way. It is an exhaustively structured solution. It provides AI-driven, highly practical, example-based Q&As that form a comprehensive framework. Because the sheer scale of this architecture is massive. We're talking about a structure spanning over 200 sections, and it caters to everyone, beginners, intermediate folks, all the way up to experienced and expert professionals. The rule of thumb here is simple. If it's in the plant, it is in this app. It really acts as a complete pedagogical roadmap for your entire career. Now, you might be wondering, how does it deliver all this content without getting super repetitive? Well, the core of this app is what they call the Studio Engine. It's this AI powerhouse that entirely eliminates the limitation of predetermined static questions. Instead, it dynamically generates a highly structured, unlimited repository of practical Q&As right when you need them. So by doing this, it actually tailors a dynamic mock interview simulator specifically to your current knowledge gaps. It brilliantly illustrates how concepts are queued sequentially. You just select your domain, your section, and then your concept, and the app continuously feeds you the next logical scenario. Because getting a question is one thing. Understanding the multidimensional answer is a whole other ballgame. The system doesn't just feed you a wall of text. Every single generated response is deconstructed into 5 distinct steps. It actively highlights the critical responses you absolutely must deliver and warns you of the hidden pitfalls. Now, they represent only a minor part of the unlimited Q&As available in the app, but they serve a very specific, crucial purpose. They perfectly simulate real-world office arguments, differing viewpoints, and intense technical debates. Because let's face it, engineering isn't just taking a test in a vacuum, right? It's about navigating heated arguments and proving your technical acumen when challenged by your peers or your superiors. And a massive part of these sessions is the power of roleplay. After every mock interview section, videos feature AI-generated live roleplay interview sessions complete with feedback on pertinent domain subjects. Giving real roleplay interviews after enriched technical discussions acts like an incredible catalyst. It is a tremendous confidence booster for any aspiring candidate, consolidating everything you've learned into practical, real-world readiness. Which leaves us with one final, very important thought. What step are you going to take right now to engineer your own success? Mastering your craft is a lifelong pursuit, and with tools like this at your fingertips, the depth of your knowledge truly has no limits. I highly encourage you to check out this combined integration of texts, text-to-speech audio, videos, and live role-play interview sessions. The tools are definitely out there to unlock your potential. The only question is, are you ready to use them?